everyone. Thank you so much for watching another episode of the Weaviate Podcast. I'm super excited to welcome Xiaoqiang Lin, a Ph.D. student at the National University of Singapore. During his time at Meta, Xiaoqiang led the research behind REFRAG, Rethinking RAG-based Decoding. We're super excited about this work at Weaviate, and I can't wait to dive into this further. Xiaoqiang, thank you so much for joining the Weaviate Podcast.
Yeah, great to be here.
Awesome. So could we maybe kick it off for people who aren't already familiar with REFRAG and what it is, the key innovations? You mind maybe sort of giving the helicopter elevator pitch of what it is?
Yeah, sure. So basically, REFRAG is an early attempt that I did to accelerate the latency in retrieval augmented generation. So specifically, if you think about the current RAG systems, right, the latency is pretty high, especially when you talk about doing this search agent, right? You have so many search results from the Google search engine or Bing search. You have so many search results, and you put those search results in a prompt, and that makes the LM inference really slow. And the result of that is that user will be having very bad experience because they have to wait very long before you get the answer. So REFRAG is really an early attempt to address this issue and try to accelerate the LM inference, specifically designed for RAG system, so that user can have better experience.
Yeah, amazing. I think there's so many cool details to it, like you kind of mentioned the sort of time to first token improvement, and overall, I think there's a really interesting topic to go down about time to first token versus throughput. Do you mind maybe just sort of explaining this concept of, say, you have the 256 token chunk in the vector database, and then within it you have, say, 16 token chunk vectors, and then you also have the token vectors. Maybe just explain this sort of like multi-granular representation.
Yeah, sure. So basically, in REFLECT, right, the way that we design the system is that we kind of borrow the idea from the vision language model, where people treat vision like images, right, as a modality, and they kind of use an embedding or a single embedding or several embeddings to represent certain images. And it's kind of similar idea in our case because we treat chunk as a new modality, right? And the way that we put chunk in the system is not by putting the raw tokens, like what we did for normal RAG system, right? We just keep all the tokens from the chunk in the decoder input, and then we just generate the answer. The way we do it is that we transform those chunk into one single embedding or several embeddings, so that we instead of using the raw token, we use those embeddings to generate the answer directly. And the benefit of doing that is quite intuitive, because if you think about raw tokens, right? Let's say you have a chunk with 16 tokens. It will take 16 tokens. It will take 16 embedded a token in the context, right? And that's really undesirable because you could have so many chunks, and that would make the context super long. But the way that if you do it in our way, instead of putting 16 chunks directly in a decoder, now you can use one single chunk embedding to represent the whole chunk, and that would only take one single position in a chunk embedding in a context window, right? And so this is a reduction by 16 times if you think about it, right? Let's say you have 16K context. After using our REFRAG, you only need to put 1,000 tokens in a context. And that's really a significant reduction in terms of the prompt, the length of the prompt. And that's really why we could have those significant performance boost from our evaluations.
Yeah, it's super interesting. And I had a lot of fun playing with these numbers too, mentioning going from 16,000 token vectors down to 1,024 chunk vectors when using, k equals 16, but say you use k equal 32, and now you have 512 vectors. So you just think about the reduction in the input length from 16,000 to 512, and yeah, it's really
Yeah,
amazing. And I guess
exactly.
it just really inspires your imagination. As I mentioned, I was playing with these numbers a little bit, and I went up to thinking about like 65,000 down to 2,048, or 262,000 down to 8,192, as I'm just multiplying numbers by two and then dividing by 32. But so
Yeah.
maybe my first question is, or not my first question, but like just continuing on this. Maybe even jumping ahead a bit, but what do you think about sort of the limits of this compression? What kind of things are you seeing as you really push long context scaling with refrag?
Yeah. So actually, we did a lot of experiments in the early exploration stage, especially in the beginning. The initial idea is to use one single embedding for the whole chunk. And let's say like in normal rack system, right? Usually one chunk could contain, several hundred to one K or several K tokens, right? One single chunk could contain that many tokens, right? And initially we want to use one single embedding for the whole chunk. And it turns out that the model doesn't work. It doesn't work at all because you are looking at a few hundred to 1,000 compression rate, and that's really the limit of this kind of system, because we want to have a big compression rate, but we would also want to have good quality, right? We want to have a model that have the performance that almost match the original model before the compression, right? So initially we were thinking, oh, maybe this is because the compression rate is too high, that the model is not able to reconstruct the information from the chunk embedding. So what we did is that we kind of reduce the compression rate from a few hundred to 100, and we further reduced the compression rate down to 16 and 32. And so what we found is that if you use the compression rate of 32, your performance would be comparable to the performance of the language model that doesn't use any compression. But if you exceed that 32 compression rate, you would have a major performance degradation. And that's really why we use this 16 and 32 compression rate, because we are looking at this performance frontier, right? We want to have low latency, but at the same time good performance.
Yeah, amazing. I think just kind of one question I have that transitions right from this is the idea of quantizing the chunk vectors. And so maybe I don't know what sorry, I missed this detail when I did read the paper thoroughly, but I missed this detail about what kind of quantization is used on the chunk vectors. You think you could say use binary quantization and things like this to further take down, say, the storage overhead, as well as what might be the losses as it goes to the decoder?
Yeah, so in our refrag, we actually do not do quantization for the chunk embeddings, and the main focus is on the compression of the length of the input, and the quantization, like we should the quantization is considered when we try to do the pre-computation, right? Think about the vectors, right? If you want to pre-compute the vector for those chunks, we would have to think about how to quantize these chunk embeddings so that we use very few memories in the disk to store all these pre-computation result. And in the inference time, we could use those pre-computed vectors to do the inference directly. And but we didn't focus on that because our work is mainly focusing on the length of the input, and all those quantization method that you see out there can be used to further reduce the memory requirement for our system. But one thing that I wish to mention is for refrag, right? We actually provide two kind of result. The first kind of result is that if you do pre-computation for all the chunk embedding, right? Meaning that for all the chunks, you pre-compute all the embeddings. And then at the inference time, you just retrieve these embeddings and then generate the result. The other way to use our REFRAG is that you don't do pre-computation at all. You compute all these chunk embedding on the fly, but in parallel. So for that scenario, we also observe significant latency improvement compared to the uncompressed version. And the main reason for that is because for our refract, right, we don't do a lot of self attention in the pre-fill stage. Think about our architecture for tokens that is not in the same chunk, right? They will never attend to each other, and this is a reduction in the number of calculation for the pre-fill stage, right? So even if you don't pre-compute all the embeddings and you do the computation on the fly, you still get a very significant performance boost. So that's something that we found is pretty amazing, because think about the production system, right? A lot of time, if you store all these chunk embedding, it will be a huge cost for the memory, right? Because you have so many chunks in the internet, and if you have to pre-compute everything, that would be a very significant cost. So a lot of time, what people do is that they pre-compute the chunks that were most frequently accessed, right? Like maybe top 10%, top 5%, and then at the inference time, if the query accidentally hit all the cache in the memory, then you could just use those vectors from the memory to do the inference. But if it doesn't, because they are 95% to 90% of chunks that were not pre-computed, right? You will have to compute the chunk embedding on the fly, and our method could also accelerate in that use case, which means a lot for the production system.
That's really cool. I'm already loving this podcast. I've already learned quite a few things, and yes, I love that idea of only pre-computing the top 10%, top 5%. We have ideas like a vector cache and Weaviate and things like this of keeping in memory certain nodes that are often expanded. So there was one detail you just mentioned that I didn't understand that well when I read the paper, which is you're mentioning that I think it's the block diagonal attention, and you mentioned in pre-fill chunks don't attend to each other. So that means you have a custom kind of transformer for this part. Do you mind maybe just explaining that further for people who don't understand these transformer architectures as well?
Yeah, sure. So think about a specific use case. Let's say we ask a question on who's the president of the US, and you could get 5 search results from the search engine, right? And the way that people usually do RAG is that they just concatenate those 5 chunks into one single prompt, and then the whole prompt is given to the transformer. And when you do the prefill, right, what the transformer will do is that when you calculate the KV cache, it will calculate the attention value between all the tokens in the prompt. So basically self-attention, right? Multi-head attention. And when you do that, it will calculate all the pairwise attention value in the whole prompt, right? So that means any tokens in the prompt, like let's say any 2 tokens in the prompt, they will be attend to each other when computing the KV cache for the prefill stage. But in our case, think about the chunk compression, right? The whole chunk is compressed into one single token embedding before we feed it to the decoder, which is like Llama and those models, right? So when you do this compression, the tokens within each chunk, they will attend to each other in the encoder, right? In the encoder, they will attend to each other and arrive to a final chunk embedding. But in the decoder, only chunk embedding will attend to each other, not the token within the chunk, right? Because those tokens, they are compressed into one single token. And that means only chunk level, like they only attend to each other in the chunk level. And this will reduce the attention calculation by a lot. And we argue that this reduction in attention calculation is actually is good because the attention calculation itself for the tokens from different chunks, they are redundant. They are not necessary because we have visualized these attention values, and we eventually find that these attention value, they are very small and they shouldn't be calculated in the first place. So that's why we have this argument here.
Yeah, so I think with that argument, it's kind of interesting. Like when I first started reading REFRAG, I always do. I'm sure everyone does this now. Is you give the paper to Cloud or ChatGPT and Gemini, whichever language model, and you say, "Hey, could you summarize this?" And this was all the language models. This was their favorite takeaway: is this kind of motivation of there's redundant information in the retrieved context, and therefore that's
Yeah.
why you have this shortcut around attending over the context. So because, and then from our experience at Weaviate, I definitely think there's a lot of like you're ranking the candidate documents by their relevance to the query. There's oftentimes there isn't really some sort of like diversity mechanism in there. But and I don't mean to stay on this topic too long, but just do you think this is because retrieval doesn't have too much sort of like relevance to deduplication, sort of, and maybe if you had like a diversity, like a maximal marginal relevance or something that's trying to promote diversity in search results, maybe this would change it a little bit. And I think it'll. Sorry, this is a long-winded question, but I think as we talk about this RL for selective expansion, and this is such a big part of this, but yeah. So sorry, I don't know what the question is in that. Maybe just like sort of, do you think if there's diversity mechanisms in the search results that might change it a little bit? Yeah.
Yeah. So actually, for the IO policy, it's not really relevant to the diversity consideration. I would say like the diversity consideration you mentioned is really practical. You are right. A lot of these RAG systems, right? In the final layer, they will do dedupe. Basically, if two chunks they are too similar, they'll kind of cut one off, one away from the final result, right? And that would actually affect the attention values between different chunks, right? This is really why we were saying that for tokens from different chunks, right? They have smaller attention value because those tokens they're actually from very different sentences, right? And and if they are not coming from the same natural language sentence, right? They are from different snips from different articles, right? So that's really the fundamental reason why these tokens, when they attend to each other, they have very low attention value because they are not from the same sentence or the same article. So that really affect the attention value in the preview, and also why we would want to do the compression, right? Because these attention value they are redundant. And on the IO policy, it's really a different consideration. So the reason why we were thinking about this IO policy is because when we train our model, right, we figure out that for the chunks with very complex information, the decoder wouldn't be able to understand it very well. So let's say for one chunk, if it contains numbers, and we ask the decoder to repeat the number using that chunk embedding, right? What we observe is that the numbers they will be the decoder wouldn't be able to reconstruct the number exactly, especially if the number is super complex and very long. So that's really make us thinking that maybe this compression is not perfect, right? Because even though we match the performance or like have a very small degradation in perplexity, but when we actually use a model, the decoder cannot understand complex chunk information, especially when the chunk contain very complex information. So we have the idea that not all chunks they are created equal, because some chunk they have more complex information than others, like numbers. But some chunk they only contain semantic, high level semantic, right? And in that case, we believe that for those chunk embedding should be sufficient to express the high level stuff. But when it comes to those very detailed numbers and very detailed informations, we think there are more entropy in those chunk, and we shouldn't compress it, because doing compression really hurts those very detailed information, and a decoder wouldn't be able to repeat or like even reconstruct. So the RL selection policy, the RL selective compression is really to address this problem of different chunks having different amount of information. And we believe that we can train a policy to automatically decide which chunk are more informative than other chunks. And for those more informative chunks, we put the raw token in the decoder. But for the less informative chunks, we put a single chunk embedding in the decoder to represent the whole chunk. So these really further boost the performance of our model, because now we have a simple policy to decide whether we should compress or not. And that would make the generation quality much better.
Yeah, amazing. I want to come back to talking about how you train the expansion policy, but just reflecting on that idea of kind of expanding out one chunk because it contains a number. This was maybe sort of the boldest idea I sort of had as I was reflecting on REFRAG, was sort of, are vector embeddings all you need? And the sort of, so kind of I was thinking about, there's a big argument around using LLMs to extract structured data from unstructured data. Say I take the markdown of my blog and I extract date published or the authors, compared to the sort of long context. It's just, you just give all your data to the LLM, and now that all your data has these vectors associated with it, and they can expand the parts of the chunks that contain that date published information, especially as we talk about these huge compressions. Like I could have, I don't have that quick lookup, but say 262,000, I think, goes down to 8,000 tokens when you have k equals 32. And you can imagine all sorts of combinations like this, but that kind of ability to just expand out each of the chunks that would contain the date published, I think it's a really profound idea for thinking about the future of database systems with these kind of these kind of refrag long context architectures. Yeah. Yes, I guess I'd love to just get your quick take on that. If you think that like this could be like sort of, if you could scale this really tremendously to maybe this is like a totally new kind of database system.
Yeah, I think the way that REFRAG designed the RAG, right, could affect the way that we design the database system nowadays, right? So again, first, I would like to mention I'm not an expert in database, and I know very few technical stuff in this field. But I do think that REFRAG would if we could put REFRAG in a production, we could potentially change the way how we serve the RAG and the way we interact with the database. And because think about the database we use for RAG system right now, right? In the final layer, we would do the retrieval using the embedding, and we use the query embedding, and then for the chunk, and we also compute those pre-compute all the embedding for the chunks, and when we do the retrieval, we just do KNN search, right? And then to get the k most relevant chunk embedding. And but for the current system, we just throw all this embedding away, because we only put the raw token in the decoder, right? So those embeddings, they will actually throw away. And a lot of time, for those production system, they use heavy quantization on those embeddings, because for the KN result, right, they only need to get a approximately correct top K relevant result, right? So I believe that if we really want to use REFRAG, we have to reform this or reconfigure the database so that instead of focusing the chunk, the token in the chunk, we should focus on the vectors in the database. And because in our RAG system, in our REFRAG, we actually need the full precision vectors. But for the current system, those embeddings they don't really matter. They do heavy quantization, and they also do they throw it away when doing the inference. So if REFRAG really is really used in production, maybe we need to think about how we should deal with a database that focuses more on the vector itself instead of the raw tokens.
Yeah, amazing. Yeah, I think obviously kind of like with Weaviate and our vector database, we're super excited about just more use for storing vectors in this totally new application. But I'm just like sort of inspired by long context generally. I think there's sort of this really interesting intermediate query in addition to sort of KNN for like question answering. And then there's also kind of like structured retrieval where you have like an exact property or like attribute like price is a float and it's either less than 2 million or greater, like things like this. Let's say you're searching through houses or something like that. But then I think there's kind of this interesting like intermediate query where say you have a database of images and you're saying how many have a nice pool that looks like this pool, and it's like it's not something that's pre-computed. It's got to compute it on the fly, and then it's got to do it to an absolutely enormous scale. That's kind of where I see this.
Mm.
This is like another new application. But anyway, so thanks for taking that detour on me. I think maybe this topic of vector embeddings are all you need is like a funny kind of takeaway. And but I think definitely more future looking of a thing. But I want to kind of come back into the RL expansion policy and how you train it to sort of just come understand the mechanisms more. I'm very curious about the sort of sequential selection of chunks. Do you see that as being a latency bottleneck? Yeah.
Yeah, that's a good question. Actually, when we designed this our policy, right, we were thinking about the latency consideration. Because if you think about sequential selection, right, you would have to do it. So let's say we have n chunks, and we want to select m chunks to uncompress. So we have to roll out the policy for m times to eventually get the m chunks to decompress, to uncompress. So we did some optimization to mitigate that problem. And the way that we do it is that it's kind of like point network. Um, so I don't know if you're familiar with point network. The way that it does is that they only forward so for the policy network, right? They only do one forward, and after that one forward, they could automatically decide what are the end steps to take by doing masking. So let me give you an example. Let's say we have a number of embedding as input, right, to our policy network. And our policy network will eventually output a multinomial distribution on this n number of chunks. And for that multinomial distribution, in the first step, we pick one chunk from by sampling from that multinomial distribution. After we sample that chunk, we don't re-forward do another forward for the policy network. What we did is that we take the logits from the output, and then we mask the position that we already selected, and we do softmax again to get another multinomial distribution, and we sample from that for the next action. So basically, rolling out m times only means we do m sampling from a distribution that was masked and renormalized. And this is really, I think, is a quite common way to mitigate the latency in that field. So we just decided to adopt that solution because doing multiple steps, the main bottleneck is that you have to recompute the output for many times. But now we save that steps and do not add additional latency to the system.
That's amazing. Yeah, I wish. I can't wait till the sort of video generation tools get to the point where we can take that, clip your explanation of that, and then just give it to say VO, and it'll output one of those 3 blue 1 brown animations of this multinomial sampling. I think that'll be such a cool thing for these technical podcasts. So, but anyway, so yeah, sort of transitioning a little
Yeah.
bit, maybe coming out of just training the reinforcement learning expansion policy, and then and the policy itself. We could talk about this sort of like 4-stage training algorithm for training refrag. I think we maybe glossed over it as we're just talking about all these topics, but you first have this thing where you take the encoder and then you project the embeddings into the decoder's latent space, and then you have this sort of reconstruction task, continual pre-training. Do you mind just kind of explaining these stages of training refrag?
Yeah, sure. So all these stages. So the main purpose of our work is actually to develop this 4-stage training recipe. And the goal of our work is really to have a general training recipe so that we can adapt any decoder and encoder combinations to work like our system, like what we want, right? And but the main the main problem that we need to address is that those encoder model, right, they do not those decoder model, right, they do not naturally understand the embedding from the encoder. And this is because they were not trained together during the pre-training, right? So the decoder naturally do not understand the chunk embedding. We need to find a way to align the encoder and decoder so that decoder could understand the embedding information and actually use that information to help us to answer the question. So to do that, we actually try a lot of stuff. If you just train the REC SFT using supervised fine tuning on the encoder and decoder for the REC tasks. It doesn't work because the decoder would find an easier local optimum by ignoring all these chunk embeddings. So that's really why we would want to use the reconstruction task, because we want the decoder to be forced to attend to the chunk embedding, and then actually use that information to help us to generate the answer. And we find that the reconstruction task is really a good way to force the decoder to pay attention, because if the decoder could pay attention to the chunk embedding and actually understand the chunk embedding, it should perfectly reconstruct everything that was encoded in that embedding, right? So that's our assumption. And so for our reconstruction task, we just chunk a very long text and then compute the chunk embedding. And we just ask the decoder to use those chunk embedding to reconstruct what's inside the chunk embedding. And that really helps a lot for the decoder to pay attention to the chunk embedding. And during the process, we found that the curriculum learning is also important because um, they are different level of difficulty in terms of reconstruction. So think about the decoder take one chunk embedding versus the decoder take 100 chunk embedding. These two tasks, they are very different, and in terms of difficulty level, right? So let's say one chunk have 16 tokens. If you reconstruct 16 tokens from one chunk embedding, that's actually a very easy task for decoder. But if you want the decoder to reconstruct maybe 2K token from 128 chunk embedding or 200, and that's actually very difficult because the decoder was never trained to take so many chunk embedding in the first place. So it would have to learn this process step by step. So it will take a look at it will start learning with fewer chunk embedding. And as the training progress, we will want to put more chunk embedding in the input so the decoder can um, slowly adapt to more chunk embedding and eventually arrive to the checkpoint that we want. So these techniques, they are actually um, vital to the successful of the alignment. And so what we found is that if you don't do these two tasks, like remove any of these two tasks, you wouldn't be able to get a good alignment. And a lot of time the decoder would just ignore all these chunk embeddings. So we found these two stages very useful, and to some extent they are necessary in our case. Yeah. So these are
Yeah,
the
super
two
interesting. Oh, sir.
these are two main training recipe for getting the decoder to understand the chunk embedding.
Yeah, sorry to cut you off a bit. I think our latency a little bit as we stream our podcast around the world cut me off a little, or confused me a little bit. But anyways, yeah, it's so interesting to hear about the curriculum learning. I remember kind of like when Mosaic ML had their MPT 65K, and they were doing, I think it was like alibi attention and rope scaling, and this kind of thing of, yeah, we just took the pre-trained language model, and now we're introducing long inputs into the data, and that like you
Mm.
have this curriculum learning. It's something that I could see maybe being a part of the DS Pi story. I have to put a DS Pi reference in all the podcasts, but yeah. So talking, I wanted to ask more about the mechanics behind trading the decoder with the encoder. Maybe also on DS Pi, where now I really am excited about the Arbor tool and how Arbor is letting us use GRPO with models in VLLM. But to then also put the gradients from the decoder back to the encoder. So you would have to have, let's say in PyTorch, you have to use say PyTorch or something like that, right? How particularly do you implement this, where you take the gradients from the decoder and put them back to the encoder?
Yeah, actually, it's very PyTorch is really a powerful tool. You don't actually need to do anything. Just make sure that everything is uh, every tensor in the network has a gradient, and it will automatically just get a back propagate to the whole network. So what I did is that I just take the encoder output and then do a projection to the token embedding, and then put that token embedding in the encoder input and in the decoder input. So the whole system has gradient information, and the PyTorch will automatically do the back propagation for you.
Have you also maybe looked into say using like Hugging Face could make it maybe easy to, because I'm thinking about PyTorch sometimes because I'm trying to grab a pre-trained LLM and a pre-trained embedding model, and I'm trying to now throw them into my system. Do you think? Yeah, I don't know what the current state is between PyTorch versus Hugging Face and what's easier to load pre-trained weights. To just be honest, I'm mostly using VLLM, and I haven't really thought too much about how you're connecting these things. But yeah. So I guess my question would be, uh, yeah, maybe just kind of coming into the tooling. I think the big question would be when we see refrag LLMs, is the API going to have an embedding model as well as an LLM? You think? Do you think it'll be easy to sort of plug and play, bring your own embedding model, bring your own LLM, and then there's some like refrag compilation layer on top? How do you see these models sort of spreading into the market? Yeah.
Are you asking about the open source of the model, or like open source of the code, so that the community could just try on their model and on their database?
Yeah, sorry, it was just like thinking out
Yeah,
loud.
so
Maybe we could.
it's a tricky question, because I actually I have done all the work, but we are working super hard to push that to the open source community, and so just stay tuned. We would have that available very soon. And yeah, I think if you take our code, you could just run on any Hugging Face pre-trained decoder and encoder, because our model, our repo is built on top of those Hugging Face APIs and um, Transformer APIs. So you could just take a checkpoint from Hugging Face and directly use in our system to train your own encoder decoder.
And so then I guess maybe just asking about the sort of computation that might require for open source, like how many GPUs am I going to need to, and GPU hours.
Yeah. So that's a good question. Actually, for the 7B model that I tried previously, you could run it on a single machine with 8 cards, but that would take you maybe 5 to 6 days if you train on one single machine. So for the whole, like for all the training stages. So I think if you really if you don't have a lot of resource, right? For example, one machine with 8 GPUs, you could train a model very easily, but it will take some time. It will take a few days to finish all the stages. But if you have more GPUs, like maybe 8 machines with 8 cards, you could finish it in 1 or 2 days.
That's pretty exciting. Yeah, I think I'm super excited to just see the sort of releases of these models. And yeah, I'll admit I need to dive into the code more. I've been sort of looking at this from just like trying to wrap my head around the algorithm. But yeah, I'm definitely really excited to be diving into that. Yeah, maybe we could also just talk a bit more about some of the experiments you did in the. So I mean, I think that's absolutely amazing that it would take you 5 to 6 days, single machine, to do that sort of reconstruction task to align the encoder and the decoder, and this continual pre-training to get the decoder used to attending over these compressed chunk embeddings. But then there's this sort of downstream task tuning phase, and I want to just maybe ask more about your experience with evaluating REFRAG on question answering, multi-turn conversation, and summarization, and just what you think about that sort of last leg of the mile.
Yeah. So actually, in our project, we don't focus on those downstream tasks because we feel that those downstream tasks they are kind of it's actually difficult to evaluate um, on those tasks and to give a fair comparison. And but we try our best to do the benchmark on those downstream tasks, like long document summarization, where we put the whole document into the context. We chunk the whole document, and then we ask the decoder to summarize what's in the document. And we train the uncompressed llama model, and we also train the compressed model using our REFRAG. And it turns out that we get pretty good result when thinking about the send latency. So if you think about the send latency, right? For our model, we could put more context in the context window, but for the original llama model, it will have to truncate some of the context to have similar latency. So the long context summarization is really a demo task that we can immediately see the benefit of REFRAG. We could get better performance under the same latency because of having this longer context window. And another benefit we could see is from the RAG tasks that we did fine tuning. So what we did is that we collect 2 million data points that are specifically designed for RAG. So basically, each data point has one question, and then have a few chunks from the system, and has its corresponding answer. And we have 2 million of them, and we just SFT our pre-trained our continued pre-trained checkpoint on those tasks. And what we have observed is that under the compression rate of 16, right? Under the compression rate of 16, given the same amount of information to the original llama model and our model, we could almost achieve similar performance in terms of accuracy of the RAG system. And another result that I think is pretty impressive is that given the same latency for the RAG system, right? our model could consistently outperform Llama model, because given the same latency, we could put more chunk search result into the context, and that would reduce the risk of missing the information that is necessary to answer the question. So we actually observed 2% average performance boosting over multiple tasks. Definitely check out our performance table in our paper to figure out more. But those results, they are kind of demonstrations to show the potential of our work. Um, and if you really read our paper, I would recommend to focus on the pre-training part, because those are the part, pre-training and R part, because these are the part that we did like rigorous comparison without those noise in the SFT tasks.
Yeah, it's amazing. I mean, I think, but maybe if I could just get your quick take on that. There's this sort of like lost in the middle context rot. This kind of, this is, but this kind of clever architectural solution. Do you think there also might be like particular training data, like? Because I imagine it's like language modeling on the internet. The pre-training is you're predicting the next token. It's like how often is there informative content like 20,000 tokens back? Do you think it's a training data problem as well, or it's just sort of this refrag clever architectural trick that's the way to solve this?
Yeah, I definitely think that it's a combination of both. So when it comes to the performance of the language model, I would say that the data is always, the one of the most, I would say, like sometimes even fundamental. The data is really something that we care about, and especially what kind of data you want to put in the training and what would be the mixture of those data. And you are right. A lot of time, when you think about those wrong context problem, right? You would have to come up with good data, especially for those data that have very long context. But you kind of have to have uh, the data points that is very similar to finding needle in the hay, right? And that's something that I believe is important for the model training. And but we didn't do a lot of data. We didn't do a lot of data ablation in our experiment, because we in this work we mainly focus on the model architecture. But I would say like data is fundamental, and you could do a lot of fun research there in terms of how do you figure out the best data mixture, and how do you know what kind of data you need to achieve those long context capability of the language model.
Yeah, amazing. Yeah, I think it's super exciting. I guess kind of like maybe rounding out some questions. I definitely wanted to kind of talk about the time to first token improvement and compare sort of time to first token latency with overall LLM throughput latency. I think it's just such an interesting thing. Like one thing, I think there's Cerebras and Grok are these two companies making these customized chips. And I think the story is that Cerebras is faster time to first token, whereas Grok is faster throughput. And so, and also shout out to Base 10. They're doing a great job with time to first token. I think just with engineering skill and GPUs. But could you maybe just sort of explain how you understand, like just maybe talk more about this kind of time to first token versus throughput latency with LLMs?
Yeah. So actually, for time to first token, it's always a very important matrix in the production system for different companies. And I talk to a lot of people in the industry, and they are all aware of this matrix. And um, in a lot of companies, they think this matrix is fundamental for the user experience. And there are a lot of existing work that try to accelerate the LM inference, right? Some through quantization, some through you know engineering the serving of the language model, right? And also some work they try to change the attention mechanism, so that when you do the attention, the transformer would take would scale linearly with respect to the prompt, the length of the prompt. So these are the very interesting work to they already try to accelerate the time to first token in a general use case, right? In a general LM inference, and we believe that this method they are still useful um, in a lot of applications. But in our work, the main focus is that for RAG, right, we identify those unique structure there, and we use those unique structure to further accelerate the time to first token latency in the production system. And those existing quantization and serving technique, they are kind of orthogonal to our work. They could readily be applied to our work to further accelerate this time to first token. But we didn't, we didn't try uh, like all the combination in our work. And I think it will be a fun, very fun project to work on, like using all these existing quantization and serving technique to further boost the time to first token latency for the refrag. I think they could be a major performance boost. If you apply all the technique, they could multiply and adding on top of each other.
Yeah, it's super cool. Yeah, I think like I don't know, I don't want to throw out some kind of number, but I think like maybe like 300 millisecond LLM inference time is a I don't know, like ballpark, or just giving, maybe not based off it too much, but yeah, it's really cool to hear that there are sort of also orthogonal benefits to time to first token. I think there a lot of applications, like if you have a Boolean valued output from the LLM or a classification label, is sort of all about time to first token, and then compared to writing a long response, now maybe it's like somewhere in the middle, and just yeah, really interesting sort of thing to be looking at. Cool. So I wanted to sort of, as we're running out, I always anchor the podcast with the general sort of future directions question, but I want to just ask one more question about the sort of schema of the refrag vectors. And I've already learned a lot from talking to you about maybe sometimes you pre-compute it, sometimes you do compute the chunk vectors on the fly. But I wanted to talk maybe about the sort of granularity of like whether you say retrieve the search results with a chunk, and then but then what is actually passed the refrag is like the entire blog post. So it's sort of like an embed small, like retrieve, or like retrieve small, read big. Or maybe if you have sort of like a matryoshka representation for refrag, where you have like a k equals 256, but then you also have k equals 16 like nested within the 256. And so maybe just kind of asking about like how you think the future of the schema design will evolve with all these different ways you could vectorize the content. Yeah.
Yeah, definitely. I think you mentioned a few very interesting direction that I also want to talk about. So one main idea that I think people could do further exploration is that if you think our selective policy, right? It's kind of it kind of works like a dynamic tokenizer, right? We kind of decide how many tokens we want to put for certain contents, right? So in our case, for chunks with more information, we use more tokens to represent it. But for chunk with less information, we use one single token to represent the whole thing. And I certainly think that I believe that there are better way to do it. And in our case, we only do binary, right? But a more ideal case is that for the whole sentence, we can decide where to chunk, and think about a token as a bag, right? You have one bag there, and for each token, ideally you want to put a similar amount of information there, right? And we could use those dynamic chunker to decide when to cut the text off, so that this certain chunk has a unit number of information, and we do different lengths of chunking to make sure that different like each token they contain the similar amount of information, and we could also do this dynamic chunker, training it along with the decoder model so that they can do end-to-end training, and decide where to cut the text more smartly. So I certainly believe that that's a better way. That's a perfect way to do the chunking for the RAG system, and I think if it's a very interesting topic to work on in the future.
Yeah, it's amazing. It sounds like sort of the next level to that late chunking idea. I think Gina AI had came up with it. I'm just kind of struggling to recall the exact details of it. I think it's like you embed the whole context and you have the contextual interaction. I have to cut out this part of the podcast out, but we have a blog post on our Weaviate blog, and Gina has a great paper describing this. But anyways, Jiaoqiang, sort of a question I would anchor the podcast with. Refrag is obviously super exciting in itself, and maybe this is sort of your answer to the question. But what future directions for AI excite you the most?
Yeah, I think right now the agentic is really one direction that I feel is most exciting for me, because that's actually one of the reasons why I wanted to work on this project, because context management is a very fundamental problem in agentic AI. And think about in our research, we only we only consider the search agent, right? Where the environment return the search result, and you would have to do some management in the search result so that you wouldn't make the context super long. And I believe that they for the whole agentic system, there are more stuff to there are many more stuff to work on besides this specific way of doing context engineering. And for example, our refrag, we could extend this work to like different, not just search agent. We can do this refrag compression for multimodal language models, so that it could be applied to those GUI computer use agent, and it could also be applied to those um, the agent that take a lot of context information. And as I mentioned earlier, for the refrag, if you compute on the fly, you still get the latency improvement. And that means that any context, right? It doesn't have to be search result. Just be any context that is super long. You could use our technique to do further acceleration. So I certainly believe that there are many similar challenges that we could address in a agentic AI system. And reflect is one of my attempts to solve some of the fundamental problem in this system.
Yeah, that's such an amazing idea. I'll give a quick mention to Charles Pierce from Weaviate, who had introduced this idea to me in the Substack article he wrote about refrag. That was it's also number one on Hacker News for the weekend, so that was something that we were really happy about. But is this idea that like we're reading these vectors, can we also write these vectors? And like you mentioned, not just the search results coming back with these vectors, but just say like an agent is calling the get weather API. That's maybe a bad example, but say it returns the weather to you with these refrag vectors. I mean, weather is a terrible example, but say like even your email API, you're expecting even your email API to come back with all these vectors. And yeah, that's really interesting because yeah, you have like this function calling loop agent, and as it gets to 20 steps of function calling, now it's got this big message history, and it can't attend over it anymore. That's so cool. That's a really
Yeah.
exciting that kind of idea of yeah yeah like agents sending vectors to other agents. Is it like agent as a tool, and Yeah, it's a really awesome one. Well, Yajing, thank you so much for joining the Weaviate Podcast. It's really just one of the most fun ones of all time. I've learned so much from this conversation, and it just is refrag is so exciting, so much fun to dive into these ideas. Thanks again for joining.
Yeah, thanks for having me.